Good morning, everybody. This is Roger Frechette with Interface Engineering. I'm going to give everybody 2 more minutes to sign on, and then we will get started. Well, good day, good afternoon, good morning to some. My name is Roger Frechette. I'm Managing Principal at Interface Engineering, and I would like to welcome everybody to Interface Engineers 2025 Educational Webinar Series event. This is an ongoing event that has been going on for a couple of years now and will continue to go. Today we have a very exciting topic. We're going to be talking about building electrification, the end game. So we appreciate you logging in. And today's discussion, we are using a tool known as GoToWebinar Meeting Platform. We are hoping that everybody can hear us well. You'll notice that there is a tool off to the side that you can use to provide questions throughout the presentation. Today's presentation will be recorded and will be made available through our website. All audience microphones will be muted during the presentation, but please feel free to add your questions to that questions field at the end of the presentation. We'll allow some time to answer as many as we can. Any questions that we cannot answer in the 1 hour, we will record. We will provide answers to those additional questions, and those will be distributed to all attendees. So Interface Engineering is an approved AIA CES provider. So for today's participation, you will earn 1 learning unit. All attendees will receive either a course completion certificate, or if you are an AIA, if you have an AIA number provided, your attendance will be reported on your behalf to the AIA sometime within the next 2 weeks. So again, we'll leave 10 to 15 minutes at the end to answer the questions we can. So with that, without further ado, I'd like you to turn it over to today's speakers. We have 3 speakers today. Mr. Steve Dacus, who is a licensed professional engineer, lead accredited professional and principal at Interface. Mr. Cody Barkholz, who is also professional engineer, lead AP, LC, CTS, principal at Interface Engineer, and Mr. Jason Sullivan, professional engineer, lead AP, associate with Interface. So Steve, I believe you're off first. I will turn it over to you. Thank you for your efforts, and I look forward to a great show.
Excellent. Thank you very much, Roger. Appreciate that introduction. Welcome, everyone. Thank you for attending the presentation on this first day of spring, the beginning of the NCAA men's basketball tournament. So hopefully we'll keep your attention more than that. I'm Steve Dacus. I've been working at Interface for over 31 years. Over that time, I've held many roles such as energy analyst, mechanical engineer, and team leader. But I'm currently a principal in our Portland office, and I'd like to introduce Cody and then Jason.
Hello, my name's Cody Barkholz. I've been electrifying buildings now for nearly 22 years as an electrical engineer. I started out my career with Echo Electric up in northern Alberta, which is an electric utility, before transitioning to the buildings engineering side. So you'll hear me discuss a bit of both worlds, and I'll explain building electrification, but also building electrification's impact on the electric utility grids. Jason?
Thanks, Cody. Yeah, I'm Jason Sullivan. I've been with Interface Engineering as a professional engineer for most of the time for about 27 years. And I design heating and air conditioning systems, perform energy analysis, and project management.
Great. So as Roger was saying, you can add questions if you look on your dashboards, or depending on whether you have a web version or another app version of the GoToWebinar. Just add your questions in those sidebars where it says questions. And like Roger said, we'll get to these questions at the end of the end of our presentation. So just wanted to give a brief overview of Interface Engineering. We're a progressive mechanical electrical consultancy. We're known for sensitive resource use, advanced building science tools, commissioning services. We're focused on innovative engineering solutions for high performance projects, providing our technical expertise through design, construction, and then the operation of buildings. We're looking to serve our clients and our community. We create sustainable designs, not only perform beyond expectations, but also lead and inspire. Our services, beyond our core engineering services of mechanical, electrical, and plumbing design, are fire life safety, lighting, daylighting, building services modeling. So that would be like energy modeling. We do daylighting modeling as well, natural ventilation modeling, building technologies, for example, data, telecom, security, and then finally, we offer commissioning services also. So sustainability is not a buzzword here at Interface. We've got 260 LEED certified building designs under our belt. 84 of those are LEED certified platinum. It's just fundamental to our culture and what we do. So the net result of all this, though, is long-term savings and less impact on the environment. We've got 10 offices across the United States. On the West Coast, we've got Portland, San Francisco, Oakland, Los Angeles, and Honolulu. In the middle part of the country, we've got offices in Denver, Chicago, and San Antonio. And then on the East Coast, we've got 2 offices, New York and Washington, D.C. We've got over 275 employees across the company, and we're licensed in 45 of the 50 states. So as part of this being a AIA registered presentation, there's 2 things that we have to include, 2 pieces of text. The first is this course description. After this presentation is over, we believe that participants will have a better understanding of building electrification and how to design buildings that have less impact on our environment and the power grids. So here are the 4 learning objectives that are also part of this being an AIA presentation. First off, we want you guys, you participants, to understand the role of electrification. You know, identify the significance of building electrification in reducing greenhouse gas emissions and conserving natural gas resources. Second, we want you all to explore different electrification technologies. We're going to present some during the course of this presentation, but we want you to learn the advantages of heat pumps over electric resistance heating and discover climate-specific strategies to optimize performance in various building types. and in different climates as well. Third, we want to recognize opportunities in existing buildings. Obviously, there's a huge stock of electric or existing buildings that could benefit from becoming all electric. So what are the practical opportunities to electrify HVAC systems, water heating, during upgrades or renovations of those existing buildings? And then finally, we want you all to incorporate renewable smart technologies. We want you to discover ways to integrate renewable energy systems, battery storage, and grid interactive technologies to improve efficiency and resilience. This is the agenda that we're going to be going through. First off, we want to provide an introduction to the challenges that we face in building electrification. Second, understand how building electrification and the power grid are actually interconnected. Third, how we want you to show, or how we want us to show you how we believe the right way is to electrify buildings. Fourth, with an already large stock, like I said, of existing buildings, how do we adapt existing buildings to be all electric? We'll discuss that. And then fifth, looking ahead to the future, how the grid may be different in the future and how it will be adapting to all electric buildings. So first off, we got two big challenges to us in electrifying buildings. First off, there's limited natural gas resources that are being depleted and they come with complicated infrastructure that deliver that resource to each one of our buildings. So how do we deal with that? And then second, there's an urgent need to reduce greenhouse gas emissions to combat climate change. So not only the buildings themselves, but our electric grid and how we produce power. The role of buildings on natural gas consumption and emissions. So if you look at all commercial and residential buildings in the United States, roughly 24% of all natural gas consumption is from commercial and residential buildings, and 29% of all greenhouse gas emissions are from those buildings. Building electrification is really critical for conserving natural gas and reducing those emissions. One thing to note is these statistics don't even include the impacts of construction and the production of the materials used in construction of these buildings on greenhouse gas emissions. There's four overarching goals of electrification. First off, we want to reduce the natural gas consumption and conserve that resource. Natural gas isn't being created, so we want to conserve that for uses that have a lot of value to the actual society and buildings. Second, we want to enable the strategic allocation of that natural gas to its highest value uses, like I was saying. Industrial processes like hydrogen production and polyethylene production. And then also for efficient power generation to address electricity supply constraints and balance the grid during peak periods, which Cody will get into later. Also, we want to decrease building operational emissions by shifting to increasingly low carbon electricity. Again, we're going to talk about how power is generated in the United States and how we can take advantage of shifting things to those low carbon electricity producers. And then finally, we want to prepare buildings to take advantage of a future ultra low emissions grid that's powered by nuclear, hydro, and renewable power resources. Cody?
Okay, challenges of electrification. Our first challenge of electrification is the power grid constraints we're under right now. specifically with electricity supply shortfalls in some areas and regions. We basically need a realistic evaluation of electrical grid reliability and supply constraints for tackling this problem. A current example right now in 2024, Schneider Electric published their sales data, and 24%, Schneider Electric's the electrical distribution equipment manufacturer, 20% of their sales were already going to data centers. And this is mainly driven by AI growth. So what we're seeing now is data centers just basically exploding in construction. And that's going to have a really extremely major impact on electricity supply, of that availability to electrify buildings with. The next one is risk of increased emissions if electrification is done with resistance heating instead of heat pumps. So the same way we can characterize burning gas to generate heat alone as a waste of natural gas, electric resistance heating is like taking our most valuable form of energy and just burning it. So the path we want to go down is to actually have those sources of energy doing useful work and then capturing that waste heat as a more efficient use of precious resources. And then thirdly, we have the need for electrification solutions tailored to diverse building types and climates. Every climate and geographic location presents unique challenges and opportunities for us as design professionals. There's no one-size-fits-all solution, where what we basically have to work with are engineering principles that we can use to help guide us to optimal solutions. Okay, so the electricity grid overview. I'm gonna basically describe here how the grid works right now. So this is basically not the future, but the present system. So power basically flows from power plants, which generate electricity, and electricity gets moved through the transmission and distribution grids to consumers. So this entire process is managed by grid operators, and these grid operators dispatch power plants in a merit order based on their operating costs. So hydro plants, for example, have water use budgets. So they're limited greatly by exactly how much water they have or have to use. Sometimes they actually have to push water downstream. And then nuclear and coal plants are extremely costly to start up and shut down because of the boilers that they run. So they supply what's called the base load on the power grid, and they'll generate power nearly for free throughout the night, for example, just to avoid the costly shutdowns and startup procedures. Renewables are also on this grid, and they've actually made balancing the system exponentially harder for the grid operators, because they'll generate power basically whenever they can and with zero input cost. So that's led to a new phenomenon on the grid, which is negative wholesale pricing, which has emerged over the last decade, particularly in Europe, but also in all over America, essentially everywhere you have heavy renewable penetration. Okay, so that brings us to what the role is of natural gas power plants in all of this. So natural gas power plants represent 43% of total electricity generation. So you can see this is a really major part of how you get electricity in anywhere in America. So it's integrally linked to our supply of natural gas in buildings for heat, to supply and to how natural gas is supplied in buildings for electricity. And these gas plants are crucial for grid balancing because they can quickly ramp up and down. So we call them peaking plants. Typically, some of them are faster and some of them are slower. So this is a bit of a generalization. But many, if not all regions, rely on gas plants to meet peak electricity demand. So your base load plants like coal or nuclear, they keep running all night for as low as, it could even be lower, but probably average is $15 per megawatt hour. Whereas how these peaking plants work is they wait until electricity prices hit about typically $50 per megawatt hour or higher. So even though they're less efficient from an input cost perspective, they generate a lot more money to the electrical producers because they only really are burning input fuel when they're getting the most value out of the electricity that they produce. So they're less efficient from an input cost perspective, but earn more money on average per megawatt hour produced than the baseload plants do. Okay, so what are the electrical supply and demand challenges? Electrical demand is growing due to economic growth, building electrification, and heat waves across the nation. And now on top of that, a new player has hit the scene, which are these giant AI inference supercomputing sensors. So these are definitely going to continue to disrupt and impact the electricity demand that exists right now. And new manufacturing is also going to have a big role in this. And then we also have capacity reduction. So retiring coal and nuclear plants are reducing available generation capacity throughout North America. We have like a bright point sort of would be hydro is increasing, but very slowly. Over the last decade, only 1.6 gigawatts of production capacity has came online within existing power dams. And for new hydroelectric generation, only 700 megawatts have come online over the last decade. So that's, to put that in perspective, that's really just about the size of one large coal plant and way below a typical nuclear power plant. Then we have shortage risks. So some regions face electricity shortages during peak summer and winter periods, and this problem is definitely set to get worse. So we're faced with a major challenge of bringing as much electricity generation capacity online as possible, and natural gas plants are the fastest way to do this by a huge margin. So the average time from construction start to get a natural gas plant online is only 24 months. Coal power plants take 4 to 6 years and require a coal mine nearby. And hydroelectric facilities take 5 to 10 years, and they're probably the most limited on locations because you have to have obviously a dammable river. And nuclear is 7 to 10 years. So none of these other sources, traditional grid stability sources, are going to be able to really come online fast enough to meet our like very near-term demand constraints. So then we have the grid constraints. So the transmission and distribution grid can limit the utility's ability to move power when it's needed. So these transmission system upgrades also take years to construct, and they're going to be necessary hugely for bringing these plants that are inevitably going to be going online, and they have to be located for the most part quite a far away from the cities, which are using most of the electrical power. Okay, so let's advance a slide here. So what does the future grid look like, and what will its implication be for buildings? So to start at the top, electricity generation is shifting to cleaner, low carbon sources like wind, solar, hydro, and nuclear. And then that brings us to energy storage systems. Energy storage systems are being added to the grid to integrate these renewables. So utility scale battery energy storage systems can absorb power during peak renewable generation production times, especially obviously when electricity prices are negative. So you can actually be getting paid just for charging your batteries on the utility scale. And this process of buying electricity price when it's low, selling when it's high is called energy arbitrage. And a big push that we need to make to improve this process is to actually try to translate the wholesale pricing fluctuations that occur on the grid that the utility grid operator uses to dispatch different generation plants. We need to get this pricing to the consumers so that consumers can buy battery energy storage systems and run the same arbitrage operation. So right now, if you do it from a building, energy arbitrage, you're going to have like very small difference in electricity prices during the middle of the day versus the evening when it's the highest demand on the system. Whereas on the utility scale, they can actually capitalize on those price differences. So then the next advancement of the future is more flexible and resilient grid is being built to handle electrification and decarbonization. So battery systems, as well as a generous supply of peaking plants are necessary to prevent outages on the system and keep the grid resilient. Then we have efficient electric heat pumps in buildings are getting put in all over the country, and these can reduce overall electricity demand, specifically when we're replacing resistance heating systems. But as you can kind of see, we also have the issue if you're going to electric heat from natural gas, you will be adding load, but hopefully freeing up natural gas for power generation. So building electrification today will have declining emission impacts over time as the grid gets cleaner. And what this means is we want to get the buildings on the grid so that when the grid improvements happen, so when we're decommissioning all our coal plants, decommissioning in the future natural gas plants, hopefully, then that's going to just see a massive improvement on the grid from an emissions perspective everywhere all at once. Okay.
There are better ways than others to electrify buildings. From a heating perspective, electric resistance heating may seem like an obvious choice to electrically heat a building, but it's much less efficient than heat pump and should be avoided for building electrification. Electric resistance heaters like electric furnaces, baseboard heaters, electric unit heaters, etc. While they're electrically efficient in converting electricity directly to heat, they are thermally inefficient compared to heat pumps. Electric resistance heaters use more power to produce the same amount of heat versus heat pumps. Due to inefficiency of electric resistance heating, it can increase building electricity consumption by 2 to 3 times compared to natural gas heating, just by virtue of the addition of electric heat versus gas that we're looking to replace and moving in the wrong direction, and 3 to 5 times compared to heat pump heating. Due to the inefficiency of electric resistance heating versus heat pump heating, widespread implementation of electric resistance heating could and would dramatically increase electricity demand and strain the grid versus both gas and heat pump heating. In regions with fossil fuel heavy power demands, coal and natural gas in particular, like the South, Texas, Midwest, Appalachia, etc., electric resistance heating can increase overall fossil fuel emissions compared to both natural gas and heat pump. Heat pump heating is the preferred option versus electric resistance heating for building electrification. As stated in the previous slide, heat pumps are 3 to 5 times more efficient than electric resistance heating. Heat pumps are more efficient because they move heat from one place to another rather than generating heat directly. Transitioning to heat pumps from natural gas heat minimizes electricity demand growth and grid impacts versus electric resistance heating. The higher thermal efficiency of heat pumps more than offsets electricity transmission and distribution losses based on electrical efficiency associated with heat pump versus electric resistance heating. Heat pumps can provide both heating and cooling, eliminating the need for separate heating and cooling systems, which is a benefit. The higher heating efficiency of heat pumps reduces overall fossil fuel emissions from both the power plants versus electric resistance heat and in uses versus natural gas heat. The ideal heat pump solution for both heating and cooling depends on your climate. So in cold climates, ground sourced heat pumps can utilize stable ground temperatures for maximum efficiency in moving heat from warm ground to indoors. Advanced cold climate air source heat pumps can effectively move heat from outdoors to indoors at very low temperatures, but backup resistance heat may be needed for the coldest hours of the year. Natural gas heat can potentially be used as backup to alleviate power grid overloading during peak heating hours, although not ideal. In moderate climates, like much of the Pacific Northwest, air source heat pumps can provide efficient heating and cooling for most of the year. It's not as beneficial to provide ground source heat pumps in moderate climates versus cold climates or even hot climates. In hot climates, ground source heat pumps can utilize stable ground temperatures for maximum efficiency in moving heat from indoors to the ground. Also, bodies of water in hot climates can be utilized if they're available near the site. Air source heat pumps can also be an efficient option in hot climates as well. Heat pump water heaters should be noted, and they can move heat from outdoors to water and can effectively serve high domestic hot water demands in a building. Air source heat pump water heaters can also produce usable cool air that can be harvested for space cooling. There are additional areas to consider for improving building efficiency with electrification besides heat pump heating and cooling. The lowest hanging fruit really is to reduce the heating and cooling load to begin with by tightly insulated building envelopes to minimize those heating and cooling loads. So better insulation, less opportunities for outdoor air infiltration, and better windows, and by better windows meaning insulated windows, double pane, and also low E coatings to minimize the solar transmission and addition to heating, cooling load from solar. Heat recovery ventilation can maintain healthy air quality indoors while reducing energy losses associated with conditioning outdoor ventilation air. Heat recovery ventilators utilize energy recovery media to move heat from building exhaust air to incoming outdoor air, and vice versa. So heat recovery ventilation is a really effective way to both ventilate buildings and preserve some of the air conditioning or heat that already exists inside the building. Appliances like induction stoves that offer lower or higher efficiency versus electric resistant stoves can help. Heat pump dryers, similar to heat pump heaters, are more efficient than electric resistance dryer and can help improve typically residential energy efficiency. Other Energy Star appliances like refrigerators, freezers, dishwashers, etc., can help reduce energy use as well. And power generation at home, solar PV and batteries can offset power consumption and from the grid and enhance resilience for the end user, number one, with storable on-site power that can be used if there are issues or a shutdown of the grid. There's also an enhanced resilience for the grid with the ability of an end user to rely only on their power source, reducing the demand on the grid and allowing the grid to recover faster. There are additional factors other than HVAC, hot water heater, appliance, etc., selections that are key to successful and efficient building electrification. So, and one thing that we do from the very beginning is our load calculations. So we want to, careful, calculated heating and cooling load calculations to right size the equipment for maximum efficiency is a first step. Equipment that's too large can use more energy than right size equipment. Oversized HVAC systems will also be a higher first cost than smaller right sized systems. Commissioning, proper installation and setup of HVAC and even PV systems per contract documents and manufacturer's recommendations ensures that systems are operating as intended for optimal performance and energy efficiency. Commissioning, the role of commissioning, they provide a detailed third-party check on systems to ensure systems are operating as intended in design. Maintenance and education, quality maintenance program and owner education is critical to sustain optimal building performance over time. Manufacturers will provide recommended routine maintenance items to keep their equipment operating efficiently for as long as possible. And building owners and maintenance folks should follow those recommendations and schedules. Supportive policies like building codes, appliance standards, incentives like tax credits, and education efforts, sort of like what we're doing right now, can help promote electrification and incrementally improve energy efficiency in the built environments. Electrifying existing buildings. So there are opportunities in existing buildings. Electrifying existing buildings is critical to achieving emissions reductions goals overall. Opportunities to fully electrify existing buildings far outnumber opportunities in new construction, but existing buildings pose unique electrification challenges compared to new construction. From the U.S. Energy Information Administration, a statistic, about 60% of homes in the United States use natural gas for space and water heating, cooking, clothes drying, etc. and about 37% of the commercial sector uses natural gas for end-use energy consumption. Electrification of existing buildings poses challenges around feasibility, cost, and distribution. If it's time for a building owner to replace HVAC or hot water systems that are currently natural gas, or if they want to add PV, they need to evaluate if electrification is practical for their building. One area is cost analysis. Electrification may not be the lowest cost option when replacing systems and may not be feasible due to budget constraints, regardless of the enhanced energy efficiency. But improvements in energy efficiency and reduced energy costs may help offset the cost of the electrification project, however. Disruption management, a building owner will need to strategize on how to complete an electrification project with tolerable disruption of their building. Electrification may be more disruptive than simply replacing gas-fired equipment with similar gas-fired equipment, but in the effort to electrify a building, there may be some disruptions that need to be considered. Project phasing could be considered to minimize that disruption. There are many opportunities for owners to move toward electrification and improve energy efficiency of existing buildings. In particular, tax incentives, rebates, and code changes could all help promote building electrification. Heating system replacements, replacing aging gas furnaces and boilers with high efficiency heat pumps, target systems nearing the end of life for cost-effective replacements, prioritizing colder climates, buildings in colder climates with high heating demands for maximum impact. Similarly, air conditioning upgrades, upgrade older AC systems to high efficiency heat pump models, target hotter climates in this case with high cooling demands and grid constraints. You can combine both of these with building envelope improvements for maximum efficiency, and water heater replacements as well, where you can replace gas water heaters with heat pump models. Most bang for your buck would be targeting larger homes and multifamily buildings, especially in hotels with high hot water heating demands. Also, low flow fixtures and efficient appliances to minimize sizing to begin with are helpful. Additional opportunities to electrify buildings can present themselves during the life of the building. During renovation expansion projects, building renovation is an ideal time to electrify. Electric systems can be easier to implement during a renovation project than when there are no building changes occurring. Avoid moving in the wrong direction by not expanding existing natural gas infrastructure. When building systems are at the end of their life, you can forecast the end of life for building systems and plan ahead of time to replace existing gas heating and hot water equipment with electric, also include building electrification in capital planning. And Kobe, I'll hand it off to you for electrical panel and service upgrades.
Sure. When you're upgrading existing electrical services, designing the systems to be microgrid ready is essential, but it's even more essential for buildings where we're approaching net zero levels of renewables located on site. A ton of advantages all start falling into place when we have renewables and microgrid ready electrical system combined. And then the other huge item to plan for is EV charging. On the projects I'm working on for commercial buildings, once you get to around 30% of parking spaces to be electrified, you're talking about doubling or even tripling your electrical power consumption per year for EV charging.
Thanks, everybody. That's That's great information. So continuing on in that theme, we need to, for existing buildings, we need to tailor our strategies to the region that they are in and the challenges there where those buildings are. One size doesn't fit all, like Cody mentioned before. So in these high cooling demand regions, upgrading to high efficiency air conditioning could reduce electricity use by 20 to 40% at peak conditions. Typically, these HVAC systems implement variable speed compressors as their first stage of cooling. What that does is that helps modulate the capacity to match cooling loads, especially in low load conditions, and offers better part load efficiency. And again, as we've mentioned before, improving your building envelope is really good in terms of decreasing the energy demand and energy costs of a building. That you can add insulation in roofs, walls, improve glazing, and it just minimizes cooling needs through that. In regions with carbon intensive power grids, this would be like the East Coast. We want to emphasize heat pump retrofits, focus on upgrading those systems to reduce the carbon footprint first, and then second, to improve efficiency overall. And again, envelope improvements make huge impacts. Like Jason was saying earlier, right-sizing HVAC systems and improving that so that we don't have oversized HVAC systems. In regions with high natural gas prices or relatively high natural gas prices and low electricity prices, this is typically here in the Pacific Northwest where we're located, we want to promote electrification just for operational cost savings, in addition to the emissions reduction that comes as part of that. Also here in the Pacific Northwest, we have ambitious electrification goals or mandates through our energy codes. We want to leverage incentives, use financial incentives wherever they might be to encourage retrofits of existing buildings. Take advantage of financing, either from loans or grants to support those retrofit projects, or financing from performance contractors. There's some utilities that actually offer technical support or incentives for obtaining technical support. So find that expertise wherever it might be, whether it's your utilities, whether it's your local mechanical, electrical engineers, but find that expertise and the resources that to facilitate any sort of retrofits that an existing building may undergo. So wrapping up existing buildings and how to convert them or get them transitioned over to all electric buildings. First thing, building-specific electrification feasibility studies or cost assessments, like Jason alluded to. We want to do an analysis up front. Look at your existing building. Look what is available to us in the beginning and what makes financial sense. Packaged heat pump retrofit solutions need to be tailored to the building type, the vintage, as we also discussed, the climate. What climate are these buildings in? But they can be a very good solution to going to an all-electric building. Hopefully we've got partners out there in code, in authorities having jurisdiction, inspectors, planners, just city governments that streamline permitting for these types of projects. And we've also got utilities that are partners in this, and they can help streamline that process also, or integrate the retrofits with what may be happening with our AHJs. Having designers that know about electrification is great, but the actual execution of this and actual construction of it is also very, very important. So having contractors that are up on all electric building solutions is very critical to this. Workforce training in the unions and the trades, that will help develop and scale up heat pump deployment. And finally, it's got to make financial sense. A lot of times we've been on projects where we go through studies and we analyze things just to find out that some of the strategies don't actually make financial sense to a developer or to a building owner. So hopefully there are those incentives available. Hopefully you can do studies, energy studies, life cycle cost analysis that looks at the long-term benefit, the long-term goals of electrification, and show a building owner that, hey, we're not just looking at first costs here, we're looking at long-term gains. Cody?
Okay, that brings us to looking ahead at the clean grid transition. So the first step in transitioning to this grid we've been talking about is the rapid growth of renewable energy sources and bringing these systems online to the grid. So renewables are fast, clean, and they contribute greatly to lowering energy prices due to the zero input cost of fuel. Next, we have to deploy utility grid scale level battery energy storage systems. So these systems are essential for improving power quality on the grid and are essential for combating negative energy pricing. So too much negative energy pricing and we're gonna see renewables go offline, which is not what we want. We really want to maximize the use of renewables on the grid. Then for nuclear and hydro, we want the expansion of carbon-free power sources for baseload application and flexibility. So in order to replace coal, we need hydro and nuclear power plants, which take years to construct, and that's really time we don't have. So there's going to be a transition period, but that's kind of the end goal. That also applies to the next one, which is retirement of coal plants. So we need to retire coal plants and transition to gas plants for peaking and backup roles to reduce emissions and pollution. Then that leads us to strategic build out of the transmission and distribution infrastructure to actually connect and balance our clean resources. Building out the grid makes systems stronger. It's not practical to build hydro dams near the loads that we need to power. So, and that goes for basically all the loads. Switch slides here. There it goes. Okay. So what are the implications for building electrification? So emissions impact for electrified buildings is that they're going to decline as the grid gets cleaner. So this is what I mentioned about in the last section, where we want to basically get all the buildings out on the water like boats, and then when the tide rises and the grid gets cleaner, it's going to lift all the boats that are floating on it. So it's really going to make cleaning up the grid incredibly more beneficial when we get these buildings electrified. Flexible loads. Flexible electric building loads and battery energy storage systems can both help integrate these wind and solar generation power sources onto the grid. So another thing that's kind of hit the scene is Bitcoin mining. So Bitcoin mining can be used for this as well, where the utility actually has control of the power to the Bitcoin miners, so they can actually deploy them when we need load on the grid to combat the negative pricing, and turn it off to basically avoid catastrophe if we're getting close to overload. So this has actually been shown to be a useful tool, similar to how battery energy storage systems work. And then we have grid decarbonization. So electrified buildings will be critical for achieving grid decarbonization goals. This will mostly be accomplished by battery energy storage system over time, because eventually battery energy storage systems will be able to take the place, take the role of the peaking plants that are using natural gas right now. And then cost reduction. So building electrification can leverage and enable continued cost reductions in clean electricity. So that happens by supporting the renewable technology and making that practical is going to lower costs overall. And then incorporating battery energy storage systems will eventually be able to, like I said, totally replace peaking plants and smooth out the demand, which is going to reduce costs from utility to consumer. Okay. Just trying to get it to advance a slide here. There it goes. Okay. Emerging opportunities and synergies. So first one, emerging technology is vehicle to building grid integration. So this is the idea of using your electric vehicles as battery energy storage systems. So you can imagine you plug in your car at your place of work or at the mall or wherever, and then depending on how you have it set up, if the grid needs power, you're going to get paid to actually charge the grid. And then vice versa, when you need power, you can draw from it. So this is kind of cutting edge technology. It's available in buses right now, but for consumer vehicles, not much. So for example, the Cybertruck can export power from its battery system, but only in an islanding mode. So it can't just export power back out onto the grid, going to your neighbors and wherever. It really just, when you lose power, then it can start generating, which is useful, but that's kind of the beginning stage. And we're definitely seeing a lot of movement in technology on this. Okay, then that brings us to grid interactive efficient buildings. So on the residential side, we have smart home thermostats and appliances. And we have the emergence of smart electrical panels, which again will actually allow the utility to have some impact on your electric building loads. And then on the commercial side, we have dynamic response of HVAC to electricity prices and signals from the utility. We can achieve this through participation in utility demand response services, which are basically experimental right now. And then we have renewable and storage integration. So on-site solar PV and battery storage to minimize building grid impacts. Sorry, it's not advancing here. Looks like we're definitely running out of time, so I'll try to speed up here a bit. Okay, so policy and market drivers. We have building performance standards and emission limits. That's one way we can kind of bring about this clean grid transition. It's not. Another way is renewable portfolio standards and clean electricity standards. These are utility controls that offer incentives. And another is carbon pricing and emission trading schemes. These are schemes by the government to influence the incentive structure to improve investment in the best interests of society. So the idea there is you're going to actually try to bring the cost to society to the producers to influence which systems they're going to build out. Okay. Then we have utility regulatory reforms to incentivize electrification and efficiency, and federal, state, and local financial incentives for heat pumps, similar to the $7,500 EV car credit we get federally. That can actually be applied to heat pumps. Okay, so the vision for the future is comfortable and healthy indoor environments, ultra low emissions and carbon footprints, power systems that are resilient to power outages and climate impacts, grid interactive and renewable integrated power systems, microgrid designs and battery energy storage systems are what's going to get us there. And then most importantly, affordable transition that's accessible to all. Maintaining low prices throughout this entire transition is beyond essential for human flourishing, as well as maintaining support from the public. So politics can change fast, as you all know, and if the public is not on board with cleaning up the power grid and kind of keeping it resilient and sustainable, then we're not going to get there. So you'll probably see that as kind of a theme is, hey, how are we going to make this transition, but do it in a way that's going to work for everyone connected to the grid, which is everyone. So, okay, that's the conclusion. Hopefully I don't know if we have any questions. I'll take a look here.
Yeah, it looks like we have one question. It was mentioned that there are ways to offset increased costs when upgrading an existing gas building. That was a generalized statement. Can you generally describe specific programs or technical approaches that offset costs when electrifying buildings? I responded in the chat that you can do life cycle cost analysis to prove that over the course of time that the upgrades that may be planned for a building to go away from natural gas are cost effective. We also have utilities that offer incentives to convert from natural gas to heat pump technology also. So there's a couple different ways that you can prove or show that it's cost effective to convert from natural gas to heat pump technologies. I don't know, Jason or Cody, do you have anything more in regards to that?
No, I think you covered that. So
okay.
No, I don't. Yeah. Thanks.
So I'll jump to the kind of a plug for our next in the series, the educational series for 2025, which is autonomous agents and how AI will transform virtual meetings. So look forward to that on May 1st, 2025. We hope to see you there.
Great.
So Steve, Cody, Jason, that was fantastic. Thank you so much. I love the idea that our buildings will power our cars and our cars will power our buildings, whoever needs it. It's a fantastic vision for the future. But great job. Really appreciate everybody's attendance online. Again, we'll follow up with certificates and answers to other questions that come through. And for anybody that is interested, Creighton is ahead of Louisville 47 to 29 in the first quarter. So enjoy the rest of your day, the rest of your week, and we'll see you at the next show. Thank you.
Good. Thank you.
Thanks for coming, everybody.